Anybody have any questions? Some more people came in. I do have one question that I definitely want to address, but I want to see if anybody else has a question. Nope. Okay. All right. So let's take a look at this one. What was the this question right here, number 97. So this one is, all right, they put it in a spot that makes it harder than it seems. The most important thing to realize, now look. Do they actually take a sample somewhere? Okay, good. I mean, they really don't. What is the expected number of rejected coins when 280 randomly selected coins are inserted to the machine? All right. But that's a little bit evil. Even if you think that's a random sample that they've actually taken, I'll let that go. Are they asking a question about the sample mean somewhere? Right? This is all about weights. Are they asking a question about the sample mean? No. Nope. What two things do you need to have happen in order to know to change the standard deviation? They take a sample and they ask a question about the sample mean. I argue that neither one of those things has happened, but even if you think the first one did happen, the second one did not. All right, let me stop for a minute because I don't want you guys to overly freak out, but that's why I try to make a kind of a big deal about that. There's two things that have to happen. Take a sample, ask a question about the sample mean. Otherwise, we're not dealing with the distribution of sample means that need a new standard deviation then. So in number 97, here's the idea. What is the expected number of coins rejected, right? Expected number. So the actual question is asking for an average number of rejected coins. So tell me, oh, you guys, I can tell, I can feel it. It's like coming over my Wi-Fi. I've got strong Wi-Fi today. I can feel the shit coming over. If I knew the probability that one coin was rejected, that would be P, because Q would be the probability that one coin is not rejected. Holy shit, it's binomial. So how do I find the expected value for a binomial? Let me see. No. So I'm sorry, got to address a couple things. I don't know. So it's just the stated mean. Not sure what that means. So it doesn't matter if it's not a sample. If I don't truly take a sample and then ask a question about the sample mean, it's not a situation where the standard deviation has to change. That's what I'm saying. Those are the two things that tell you that the standard deviation has to change. I take a sample and I ask a question about the sample mean. That is not what happened in this problem. So now listen. Do you guys agree with me that's a binomial problem? Fundamentally, it is. Either you reject it or you don't. It's binomial. So if I just knew the probability that a coin would be rejected, that's P. Don't I know N? Yeah, 280. Can't I figure out the mean then? Yeah, N times P. So really just number 97 could have been put back in chapter 6. Stay with me now. I know I can feel people turning off. Like, I'm not going to listen to this guy. Good Lord, class just started. He's already doing weird shit. I could have put this problem back in chapter 6. I love that they put it here because we always have to pay attention to why we're changing things like the standard deviation. Why does it make sense to do that? Here it doesn't, because it doesn't meet the two requirements. They just want you to remember that. We're not changing standard deviation because we're in chapter 7. We're changing standard deviation when I have the situation where it needs to change. So that's why I love this kind of problem. This is a chapter 6 problem that they put in chapter 7, just to remind you, hey, everybody, hey, you don't always do that shit. You only do it when you need to. Does that make any sense? That is a freaky problem because they put it at the end of a section all about changing standard deviation, and you're not supposed to change standard deviation for that problem. So what you do, I will tell you exactly what to do in this problem. Using the mean they give you, using the standard deviation they give you, because I want to know the probability that one coin is rejected, which means it's not in that range. It's out here, right? So if you find the probability, it's between those two weights, and then you do 1 minus that, that's the probability that a coin is rejected. That's P. And then you multiply that by N, which is 280, and you're done. Let me stop there for a minute. You guys with me? I basically just told you exactly how to do that problem. I would love it if you understood it also. And I agree, that problem is weird because of where they put it, right? And the wording. Uh-oh. Can you say it once more? Sure. All right. All right. Let's see. How can I say that a little differently? We did a problem just like this a while back. I can't remember what handout it was. Anytime you, so if you calculate the probability that a coin is rejected, that's P, because Q would be the probability it's not rejected. Is that good? Then it becomes a binomial situation. I'm not sure how else to say this. As a student, it's really difficult for you to step outside of structured ways to do problems. You want structure, you want it, and you impose it when you shouldn't. So there's bigger ideas. I wish I could remember where that problem was. It was, I can't remember. There was a problem where we had to figure out, I think it was like, what's the number of students who would make larger than 300 something? You had to figure out the probability of that happening first, and then you multiply that by N. That's N times P. That's the expected number, right? So in that problem, let me say it one more time. What you do is you calculate the probability that one coin is rejected, right? And so let me put the problem up here again and give you a couple more pointers around this. And then that'll be the last thing I say about this problem. Let me share this. Bam, bam, bam. Let me plug this in. Bluetooth. Is it connected?
Bluetooth connected.
Well, thank you. Scheisse. All right. Life tip, kids. Learn how to cuss in many languages. So 97. Can you guys see 97 now? I'm really hoping that you're not going to tell me. Okay.
Yeah.
Oh, thank you. So there's the mean. And now something that's really evil about this problem. This problem is actually not as good as I hoped. They didn't tell you that it's got to be normally distributed. I wish they would have said that because it would have been so beautiful. It doesn't matter that this is bigger than 30 because I'm not actually taking the sample. This is a question about what if I do that. I haven't actually taken that sample. So they should have said it's normally distributed. Now I got to figure out, let me delete this real quick. Where's my eraser? There you are. Because I can't see that. Okay. Between 5.111 and 5.291, what percentage, what's the probability of a coin being in here? That would be the probability that it's not rejected, right? Is that cool? It only, if the coins have weights between those two, it's accepted. It's not rejected. So out here is actually the probability that it's rejected. So once you get this area, so you make a z-score, you look up the area, make a z-score, you look up the area, you subtract the areas, blah, blah, blah. If that was 0.9, then the probability of rejected would be 0.1, the opposite, out here, outside. And then you just multiply that by 280, you're done. Thank you very much. So there's your standard deviation. Okay, that's enough about that specific problem. If you don't get one problem, I don't care. It's the idea that you need to get. Oh, okay, good. All right. All right, guys. I'm going to clear that mess away. Any? Oh, yeah, I got to do that problem. Or that is the problem we just did, isn't it? Right. Okay, good. That's right. I got confused. It's fantastic.
Can we look at 63 on 7.1 for C?
Okay. So no matter what, so it says here the distribution is unknown, right? But the sample means for 36 taxpayers, what will their distribution look like?
Normal.
Yeah, because n is greater than
30.
30. Is that cool? So in part C then, you would put, I'm not sharing this, am I? Oh, I am sharing it. Great. You would put an n here for normal, and inside you got to put the mean and the standard deviation. Now, of course, just go away. Stop. You're not going to put, where is it? Barf, barf, barf. Here it is. 2 hours. You're not going to put 2 there for the standard deviation, right? Because you took a sample of 36. So you got to change that. Is that all right? So whenever you see this format of a question, they want to know what distribution it is, B, U, or N, binomial, uniform, or normal. And then you put the 2 most important numbers, and for normal, it's the mean and the standard deviation. Okay. Is that all right? If it's not, I can explain it a different way maybe. I sound like somebody who's trying to come to my house. Oh boy, this is exciting, kids. Gonna see an abduction live on Zoom. Some of you guys would be like, oh no, and some of you guys would be like, I guess class is over. Let me see. Oh, okay. All right, which part? The part right now about this, if you see that kind of problem, you see this all over the place in this book, right? This kind of problem. Hopefully, can you see my mouse when I do this? I'm hoping you can. Thank you. All right. Either, so the answer is either going to be, so the answer to this problem, no, Jeff, you got to tell it. Give me a minute. It's technology adds like 20 minutes onto class. I swear. All right. So this problem is either going to be like binomial NP. If it was a binomial distribution, I would tell it what N was and what P was. U, A, B. If it was uniform, so I put a U here, and then I put A, comma, B, the beginning and the end. Or it's normal, mu, sigma, because those are the 2 most important things to know for a normal curve. Is that all right? So here I'm definitely going to put normal. I'm going to put N, and then go ahead and put the mu and put the correct standard deviation here. It's not going to be 2 because I took a sample of 36. Is that all right? Is that all right? No? Okay, okay. All right. Anything else, guys? Any other homework questions? Whoa, that was close. Get out of there. I got too much crap on this table. Okay. Nothing else?
I have a question.
Yes.
On the practice quiz for when it says what would be the distribution of the mean, that's when you look at it. I know you answered normal. So you would just look at it and then from that you would get your answer from there.
Look at what?
36, it was like, what's the distribution of the mean from 37 groups?
Yeah. So when you say look at it and get your answer, what are you looking at?
Looking at the 37, is that how you got the normal distribution or no?
What about 37 tells you it's normal?
It's more than 30.
Beautiful. Exactly.
Okay.
Kabam. I like it. I got to get a better chair, man. Everybody else doing okay? Any other questions? I have now lost everybody. There you are. Let me put you back over there. Okay. All right. So let's transition into remembering what the hell we did last time and then building on that, right? So what we did last time was basically section 8.1. So today we're going to do 8.3. And I explained to you last time why that is. 8.3 also uses the z-score chart. That's why I like doing 8.3. 8.2 is going to use a whole new chart. Yay. Can't wait. All right. Get over here. The chart that 8.2 uses is actually from a person that used to work at the Guinness Brewery. So if you like Guinness, you got a problem coming related to Guinness. So here's what we did last time. Holy shit. Get over there. Got to straighten my room up. A little earthquake. Okay. Jeff, it's fine. No, I can't take it. All right. All right. I did you. You're done. All right. So last time we actually created this formula. And what this formula does, the main purpose for this formula is to give an idea of what the mean might be. We construct this interval and we hope that our interval catches the real mean. So if I make a 95% confidence interval, can somebody tell me what part of that equation does that relate to? I know this, so then I can figure out what part of this.
Z-score.
Yes. Let me improve my whiteboard a little bit. Hold on. I'll try to. Dadgummit. Jeff, I'm gonna give up in a minute. All right, I'll give up. I'll fix it later. So the reason those are connected is because I want to go far enough out to catch 95% of the data to be 95% confident that my interval actually catches the real mean. If I catch 95% of everything, I'm 95% confident I caught a certain thing. If I catch 95% of all the fish in a lake, I'm 95% certain that I caught a certain fish. Is that right? I don't like fish, but it's a good analogy. What was I going to say next? I forgot. Oh, so the mean exists somewhere. So when we do this problem, I end up with an interval from something to something. And I'm kind of, if it's a 95% confidence interval, there's a 95% chance that my interval actually contains the real mean. Let me stop right there. That's exactly what I just said about the fish, right? But now we're talking about data points. Okay. So let's try a real quick problem together. And then I got my little handout up there that I'm going to let you guys work on. Let's see. All right. Let me get rid of this. Blah, 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 blah. So let's say that we take a sample of 45 students and find an average number of Tylenol taken per day of, what do you got, Jeff? 5.92. Sigma is known to be, what do you got, Jeff? I don't know, man. 2.91. Sure. What the hell? All right. This is obviously just completely made up. So we talked to 45 students and we find an average number of Tylenol taken per day to be 5.92 Tylenol per day. The standard deviation is known to be 2.91. We want to create the 95% confidence interval for the true. And when I say true, I mean population mean number of Tylenol taken. For all students. All right, let me let that sink in. All right, now, do we have everything we need? What's N?
45.
N is 45. Where should I put this? I'll put it over here. N is 45. Do we know sigma?
2.91.
2.91. Do we know X bar?
5.92.
5.92, because that's the sample average, right? 5.92. And then how do I find Z?
You look up 95 on the table.
The baby chart? Or do you mean, how do you mean? If you don't look it up the right way, you're not going to find it. So let me tell you the full official old school way to do it, and then I'll remind you of the shortcut for this specific one. What does a 95% confidence interval look like? Can you draw it for me? What would it look like? Go ahead and try to draw. I think I already did earlier, didn't I? I did. So you just got to remember me doing it. Remember that here it is, right? That's the visualization of a 95% confidence interval. It catches 95% of the data. How do I find these Z-scores? I can't look up 0.95 because that's not the area below a Z-score. What's this area here, for example?
2.5.
Yeah, 0.025. I like it. So if you look up 0.025, what Z-score do you find? Let me pull up my Z-scores. Where are you, Z-scores?
Was it like negative 1.64 or something?
No. Thank you for playing. Try again. Where are you? Is that you? That's you. Okay. So let me show you this. So if you look up 0.025, the closest I can get is right here. You guys see that? In fact, I mean, that's it. That's 0.025. Ain't no question about close. What Z-score is at? negative 1.96. Are you guys semi with me? Not with me at all? I suck. Okay. But just to remind you guys, if instead you look here, if you look on the positive Z-score chart, this is not always going to work, especially not with me. But there are certain confidence levels that are here. What's my confidence level here? 95. So what do you get when you look up 0.95? You get 1.96, what we just got. So that's what I call the little baby chart. Am I always going to ask you one of these 3 levels? No. So you're going to have to know how to do it the old school way. But if I give you one of these 3, you can just look right here. Bam, you got it. You guys semi with me? Do you remember we got in 1.645 a few times? Remember that? No? I don't know. Don't freak out if you start remembering some of these numbers. All right. So now we got everything. We got my z-score. What am I going to put here then?
1.96.
Yeah, the plus and minus is built in. So I got my x bar, give or take 1.96 of these. So if I start at my sample mean and I go up and down this much, I'll end up being 95% confident that that interval catches the real mean because I will have caught 95% of the stuff. I'm going to erase this so I got some more room here. I'll leave the question. So let's see, we have 5.92, give or take. Who remembers what this part was called?
The error.
Good. Error. So let me see, let me do this with you, just in case there's some dissension. What do you guys get for this error?
0.850.
Yeah. Kick ass. So the general idea is the error, make sure it goes at least one more place than the mean does. That's an O, so that's fantastic because the next number is a 2. Beautiful. And now you just subtract that from this and you add that to this. And that'll give you the interval. So you get 5.07 up to 6.77. Is that right? Maybe.
Yes.
Yeah, that's right.
Thank you. All right, sweet. Let me stop. So all right. So let's do this first, and then I'll do some extra shit. I'm not done when I get here. You're done after you write your conclusion. We are farmers. I have to do that. We are 95% confident that the interval 5.07 to 6.77. Now this is the one time there's no units here. It's not grams, it's not milliliters, it's number of Tylenol pills. There's no units. So we are 95% confident that the interval 5.07 to 6.77, I guess you could say pills. I do want units on these bad boys. Contains the true number of pills, true mean number of pills taken by all students. And it should be Tylenol pills, but oh well. Not just any pill you guys find. What's this? Let me take it. Find out. So if some other group, so we talked to 45 students, right? If some other group came and picked their own sample of 45 students, do you think that their sample mean they find would be different or the same?
Different.
Different.
I would put all of my money on it being different. And that's saying a decent amount. Well, actually, I guess it's not saying much as a teacher. It's not a lot of money, but for me, it's a lot. It's what I need. So if some other group came along and made their own interval, and then another group came along and made their own interval, and another group came along and made their own interval, 95% of those intervals would actually contain the true mean. That's why we're 95% confident that ours catches the true mean. That's why when you word this bad boy, it better be worded like this. We are this confident that our interval contains or catches the true mean. I like it. Don't say we're 95% confident that the real mean is in here. That's not right. That's not physically what happens. Okay, maybe. I know you guys love this. You're eating it up. All right. All right, so let's do this. Oh, let me talk about one more thing before we do this handout. If I would have made a 90%, if I would have made a 90% confidence interval, would that interval have been wider or narrower than this? If I make a 90 instead of a 95, would it have been wider or narrower?
Wider?
Narrow?
Narrower. It would have been narrower. Yes. Because how much data would it have to catch to be 90% confident? I'd have to catch
Less?
90%. So I'd have to catch less data. I love it. So wouldn't I have to have not as big of a fishing net if I want to catch less fish? So I think of data as fish. I guess that makes sense. I don't want to eat data. I don't want to eat fish. It's perfect. I like it. Don't eat the data. All right, all right. So the other thing I want to talk about is this bad boy. All right, so I'm going to erase all this here in a minute. My God, I really make use of the space I have, don't I? Wow. All right, I'm going to erase all this. It's going to go away. Bye, problem. Bye. I don't see anybody yelling. Okay. Good to know you, problem. Get out of here. So this part was the error, right? So I'm going to create a little, doesn't the error equal this? Is that cool to say? Are you guys cool with that? That's what I just said, isn't it? That's the error. So that's the error. Okay, Jeff, you said it twice. Way to go. Can you solve this for n? Do it. Algebra coming at you. Solve this expression for n. I'll just stand over here and be useless for a while. I think this was on our warm-up sheet. Remember that? About 3.7 million years ago, we did that warm-up sheet. So what sucks about solving this for n? There's a couple of things. The main thing is n is down here. That kind of sucks, right? So what was somebody's first step to solve this for n?
Multiply both sides by square root n.
Yeah, so one of the worst things about this whole equation is there's a fraction in it. So I could just kill my fraction, fraction. And then I'm going to divide by e. So see how these just switch places? Kind of nifty. And real quick, little side note. What is 10 divided by 5?
2.
Oh, no. Oh, yeah. What's 10 divided by 2?
5.
5. No way. See how they just switch places? The 5 and the 2 switch places? Of course they do. 10 divided by one chunk is the other chunk. So I could just make these switch places. I'm going to divide by e now. And so e is down there now. So they really just switch places. And then what's the last thing I have to do to solve for n?
Square both sides.
Yeah, I got to undo a square root. So n equals this mess. So what the shit? Nice job, Jeff. Just like a math teacher, go playing around with freaking letters and feel all big and important. Look at me, I can play with letters. So here's what this formula is for. If I know how off I want to be, I want to control my error. Doesn't that sound like something you would want to do? I want to control how off I am. How big of a sample do I have to take to be this error? So somebody help me out. I should have written this down. I'm going to erase all our work here. You only have to do this once because now we have the equation. What was the problem we just did? N was 45. Did somebody write down what was the error that we got? Remember, there's 5.92 plus or minus. I can't remember.
0.850.
0.850?
0.850.
Okay. So an N of 45 leads me to an error of 0.85, right? That's what we just did. That problem we just did a minute ago. So what if my boss says, Jeff, that's way too much error, dude. I need it to be 0.1. I'm like, oh shit. I got error to be 0.85. He wants the freaking error to be 0.1. Holy shit, boss. So now I got to figure out, well, how large of a sample must I take so I can get the error down to 0.1? It's going to be a lot more than 45. So let's figure it out. So what will the sample size have to be? Now, N equals, Z was 1.96, right? The standard deviation was 2.91 divided by my error. I want it to be 0.1. And then I square all that shit. Let's see what we get. I'd say about 3,500. But I don't know. That's up there in the 3,000 somewhere, I think. Yeah, I'm close. I want you to really understand what I'm saying here. That first problem we did, for a sample size of 45, it led to an error of 0.85. So how do we decrease the error? How are we more sure about what we see? We take a larger sample. We knew that on the first day. You guys knew that on the first day. A bigger sample, better, Jeff. Bigger sample, better. So that's all this equation does, is it says, all right, if you want to be this good, you're going to need a much bigger sample, right? We're going to need a bigger boat. So anybody have that answer for me?
3,253.105.
Thanks, Jenny. I saw somebody start to enter it in. They're like, well, shit, he's got it. Let me see. Yeah, I got 3253.1. Doesn't really matter. Blah, blah, blah. Isn't this 0.5, blah, blah. Wasn't this, I've completely, oh yeah, number of pills. So what we normally do is we round it to the next number up, 3254. I mean, sorry, this is number of students and the pills they took it on. I don't want to take 0.105 students. I don't want to have to chop somebody up. I don't want to make you guys into little Dexters running around taking exact samples. We just round up to the next whole number, right? Don't chop people up, kids. All right. Don't chop people up and vote. Do those two things. Okay, so. That is the formula. If they ask you, how large of a sample would we need to be within so much, that's the formula you use. So then we can figure out, is that feasible? Is that something I can actually do? Instead of talking to 45, can I talk to 3,000 too? I don't know. It depends. Right? So I call this a feasibility study sometimes, if you know what the word feasible means. So.
Can you explain really quick? Sorry, my bird's screaming. Can you explain really quick what the equation we just created means again?
Oh, this equation.
Yeah.
for a given confidence level, if somebody tells me how close they want it to be, what the error is to be, I can figure out how large of a sample will lead to that. In fact, real quick, let me see if you guys get anything out of this. If I were to put into this equation, oh crap, you're a dead one. Go lay down. All right. If I were to put into this equation the numbers from this problem, so error was 0.85, right? So if I were to put in this 1.96 times 2.91 divided by 0.85, let's see what we get. I already know that a 0.85 error should lead to a sample of 45. I know those go together. We did that problem. But let's see, what do we get when we do this? I don't know, Jeff. Well, actually, I do know. But yeah, buddy. When you do this, you get 45.02. So you round it up to 46. It's almost 45. It's a little bit off because we rounded this. I know that this error goes with this sample size. So what this equation does for me is, if somebody says, I need the error to be 0.03, I could figure out how big of a sample I need to take to make that happen. Because what happens to the error when this gets bigger? If this piece gets bigger, what happens to this whole piece here? Mathematically.
Get smaller?
Yeah, if I'm dividing by more, my result is less. So if my error needs to be tiny, my n has to be big, which makes sense. Again, we knew that in the first day. The bigger the sample, the more sure we are about what we see. That's all that says. It's just the mathematical expression of that statement. Okay, so let's do this. Let's look at my dolphin problem. I have a dolphin problem. Sounds weird, right? Got my backyard, there's dolphins out there. It's crazy. I'm gonna call in somebody. No, here. Where'd it go? Scheisse. So up on in Canvas, where'd you go, Canvas? There you are. Oh my gosh, there's so many freaking things to keep track of. There we go. Hold on, everybody. So if you want to, if you're able to, go to Canvas, go to Modules, go to Unit 8, Craziness, Section 8183. And then you'll see the dolphin problem. Dolphin problem. All right. So go there now. Go to, so I'm going to open it up in a different way. Is that the way I want to open it up? Yes. I like it. Don't forget to vote, everybody. Go vote. Do it. Or, you know, mail in is best. Uh-oh. Is everybody able to access that on Canvas? Are you guys, anybody not able to access that? That's actually here right now and not in bed or something? All right, so do it. Do it. Do this problem. Just worry about this one side. This is all we've done so far, Section 8.1. So just the dolphins. And I'll just sit here. Let me stop recording for a while. Everybody should be back. Thank you, lady. Let's see, where are you? There you are. Okay, so let's take a look at this. Here's my dolphins. And it's not a bad idea to always summarize all the parts that you're told. So we know the average length is 92.6. Population standard deviation is 4.11. And I take a sample of 37. Why is it okay to use z-scores here?
Sample
do-
size
Yeah,
is large enough.
big enough, greater than
30.
30, sweet. And you don't actually have a lot of work to do because we just did a 95% confidence interval. And what was the z-score there? It was
1.96.
I like it. So 90%, 1645, 95%, 1.96. Anyway, we're going to see a lot of those. And now we got everything we need to throw into the old formula. So we just throw it in the old formula. Got 92.6, give or take 1.96 of these the steps, which will be 4.11 divided by a square root of 37. Kind of makes sense that this is built into the equation because we took a sample and we're talking about the sample means. Therefore, I need the correct standard deviation. Oh, shit. At that time, catch up on emails. I probably should have. Let's see. What do you guys get for the error on this thing?
1.32.
Yeah, so you get 92.6, give or take 1.32. Is that cool with everybody? Good, because it's the right answer. And then when you do that, you get the little interval. What would that be? 91.28? Is that right?
Yes.
And then 93.92. All right, so that's the confidence interval. And of course, you're never done until you actually write your conclusion. So we are 95% confident that what? Who's somebody I haven't heard from yet? Anybody written that down yet? We're 95% confident that what?
The interval 91.28 to 93.924 inches.
Yeah, I like it. 91.28 inches to 93.92 inches does what?
Contains the true mean number of a dolphin.
Contains a true mean what of the dolphins?
Number of inches.
We could just say that. It's interesting to me. Well, anyway, I'm not picking on you, but I love it how when you're writing this thing, suddenly we sort of get detached from how to just speak. So it contains a true mean length of dolphins, right? This wasn't anywhere specific. No. Bam. What chance is there that the true mean is not in here? What are the chances that the true mean is not in here?
5.
5%. I love it. Cool. Is everybody good with that problem? You guys all right? Okay. Now, this kind of problem, I normally wouldn't even ask you to make the interval, but I just decided to do it for more practice. But would it be smaller or larger? You don't actually have to do the work. Would it be smaller or larger?
Smaller.
Smaller, because same reason as before, right? We have to catch less stuff. So the only thing that changes in all the in this equation, what piece of that's going to change? This equation here.
Z-score?
The z-score is going to change because that was the z-score for 95%. What's the z-score for 90%?
1.645.
Yes. Oh my gosh, Jeff. If Jeff could write, you guys would have a much easier time. I'm so sorry. You chose poorly. 92.6, right? I've gone and forgot. There we go. Yeah. Plus or minus 1.645. I only have to go out this far, not this far, if I only want to catch 90% instead of 95%. Times 4.11 divided by the square root. It's all the same formula, except I don't go as far out. I only go out that far. because I only want to catch 90% of the stuff. So now my error will be, I don't know.
1.1.
You guys, who to what?
1.111.
Yes, cool. 1.11. I like it. You can go further if you want to. I only have to go one more place. So then that would be from 91.49, is that right? To 93.71, maybe?
That's what I got.
Sweet. All right, thank God. I didn't really ask for the, but it would be exactly the same as this, except you would use those numbers and you would say 90% confident. So maybe I should write it. We are 90% confident that the interval, by the way, it always drives me a little crazy when people pluralize this. There is one interval. An interval is defined by two numbers, a beginning and an end. One interval, no intervals. That the interval 91.49 inches to 93.71 inches contains the true mean length of blah, blah, blah. How far would I have to go to be 100% confident, theoretically?
10%.
No. How large would the interval be to be 100% confident, theoretically?
3 standard deviations.
Nope. It would
Is
be
it
from negative infinity.
infinity?
Oh, is somebody saying that same thing?
Yeah, I said infinity.
Beautiful. Good job. So that would make 100% confidence theoretically. Now, when I'm talking about something like dolphin length, there's not going to be a negative length of a dolphin. So that's why I said theoretically. So this would be from 0 up to whatever makes sense, right? The biggest dolphin that could fit on Earth. The dolphin that ate Manhattan. I don't know. Watched too many old sci-fi movies. Yep. So for the question, with a 90% confidence will be smaller, we write smaller because not because it's nothing to do with calculated. It's because it has to catch 5% less stuff. So if I have to catch 5% less stuff, I'm going to go out a little less far. It's going to be not as wide. It doesn't have to catch as much. So in the picture, this is 95%. So where would 90% be? Become a 95. Oh my gosh. I know I write poorly, but good Lord. There's 95. Ooh, look at me. That's good job. Good job. And 95%, I'm sorry, 90% would be a little bit less. I only have to catch 90% then. Does that make sense? That's all. That's it. If I catch 90% of the information, how confident am I that I caught a specific piece of information? 90% confident. Does that make sense? Or does it not make sense? Let me ask that. Somebody's chatting. Okay, cool. I like it. Now, don't take my tone wrong. I know this is new. This is weird. But it's built on such easily thought of terms. That's why I talk about the fishing net. I mean, you can think of this very physically, very easily. Catch so much data. So you got to go further if you want to be more confident that you caught something specific. So that it makes the net bigger. It makes the interval bigger. So you catch more fish. You catch more data. It's so physical. It's awesome. And then this last problem at the bottom. I wrote the formula a little bit differently. This is still the same formula. I just distributed the square for some reason. But I want to be within 0.5 inches at 95% confidence. So what's the Z going to be for 95%?
1.96.
Yeah. And the sigma is the same as it was. So here's 1.96. I'm going to use the original formula, the square outside. Where's this go? Oh
On
my
the
gosh.
denominator.
What is happening? Oh, I see what I just did. Hold on, guys. Let me clear this. I'm using the wrong drawing tool. That's just awesome. Let me catch back up. Sorry. So I got my 1.96. I love it. That is the error. The magic word is within. They're not going to always use the word within, but that is a clue when they use that word. I want to be off by, I want to be off by at most, I want it to be within. That's the key to be the error that goes down here. And of course, the standard deviation is the same as it was before. What was it, 4.11? Yes. So are you cool with the fact that that's just the, if you distribute the square, you get that? It doesn't matter. You could do it either way. I prefer this way. So what do you guys get for that?
About 260.
Yeah, so 259.57, blah, 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 rounded up to 260.
Gotcha.
Now, how many dolphins? 37 dolphins led to, so 37 dolphins led to an error of 1.32 inches. So obviously, if I only want to be half an inch off, I'm going to have to take a lot more dolphins to be more certain about what I see. That's the idea behind that problem. Okay. We got one last idea to go through, gang. It's related to this next bit down here. Look at that funky thing. All right, we're going to develop that. Don't worry. Any questions about this work up here about the dolphins? We need Sarah McLachlan to come out. Have a song about the dolphins. In the arms of the nation. Please give. All right, sorry. Sarah McLachlan. I know she's all about the puppies. All right, let me stop sharing this. So now I want a way to do this, but for percentages. And this should not be a big surprise because that's actually the one we see the most. So if they say like 40% are going to vote for this person, 44% are going to vote for that person, always at the bottom of the screen or the article, whatever the shit, it says plus or minus 4%. And they didn't just go, I don't know, we're off by like 4. No, it came from the situation. We're going to actually learn the formula to figure out what that should be, the plus or minus whatever. We're going to learn it right now. And I know you're just as excited about me. Uh-oh, did I miss a question? Oh, you got it. Okay, thank God. I didn't miss a question. So the very first thing I want to ask you is these are going to be kind of NPQ related problems, right? Because I'm going to make a confidence interval. I can make a confidence interval for the percentage of people that are going to vote for somebody, which means there's a probability they'll vote for that person and there's a probability they won't, P and Q. Are you guys with me so far? Nothing major there. It kind of makes sense. The letter P that we use, this guy, actually is the population probability of success. So just like we have a mu is the population mean and X bar is the sample mean, right? We need to have a different thing if it's not a population probability. So here's how that works. Oh shit. Okay. So P is population probability or percentage. You ready for this? You're gonna love it. P hat is the sample percentage. P hat. P with a little party hat. Right? P hat, the thing you don't want to have to wear. Just want to get that out the way now. I know it's just weird. I think the book uses a different symbol. I don't give a shit. We're all going to use the correct symbol, which is this. So I really want you guys to get it. Mu is population mean, X bar is sample mean. We know that. So these work the exact same way. P is a percentage that comes from a population. P hat is a percentage that comes from a sample. That's all. So now watch this. For an NPQ problem, mu is NP. So what's X bar? Why is mu NP? Because P is the population percentage. So what would X bar be?
NP hat.
NP hat. All right, we're doing good so far. Oh, shit. All right, so here's what's going to happen. Now that we've got that down, P hat just means sample percent, the same way X bar. See how we put a little thing on his head? Put a little thing on his head. Anyway. So if I start in the same place I started when we developed the other confidence interval formula, which is right here. You can do it, Jeff. There it is. There it is, buddy. Good job. All right. We started here to develop the formula we used. I have no idea if you guys remember, but we did. First thing we did was replace that with X bar. But now I know that that's NP hat. Can somebody remind me what that is for an NPQ problem? What's the formula for the standard deviation for an NPQ problem? I basically just gave it away.
Square root of NPQ.
NPQ. So what's kind of like this guy? Let me see, how do I want to write this? Yeah, sure. What's this guy? It would be square root of NP hat Q hat. Oh yeah. So that's what I'm going to put here. So I started with the exact same formula and I put all the NPQ shit in. And remind me, and this is a little X bar, what is this trying to do? Is trying to capture the mean, right? Right? That's what I'm trying to do with. That's what I'm trying to do with this guy. Is I'm trying to capture the mean, right? So what am I? So this is I'm trying to capture the mean, which is NP. Just stay with me. I know this is weird. The nice thing is we only have to do this once, and then we're going to develop a formula that we could use, and you don't have to do this by yourself because it's very straight. All right. What kind of sucks about this? I want to get to a point where I could say 40%, give or take 4%. I want percent, and this is right now not a percent because it's multiplied by n. So let me just divide everything by n. Yeah. So that goes away. So now I'm capturing the percentage, the population percentage. That makes sense. That goes away. Now it's going to be my sample percent, give or take. But this is weird. Can I just kill those ends? Just let me kill them. Let me just kill them. Can I just kill those ends? Correct? Good. I see somebody shaking it. Hell no. And here's the simplest reason why not. That's an n. That's half an n. How would they cancel? They're not the same. Isn't that half an n? Square root? So here's what I can do. N is equal to the square root of n squared. Think about it. What's the square root of n squared? N, especially because n is positive. You can't have negative things. Math is the reason we can't have negative things. I want that on a shirt. Anyway, so the reason we can't have nice things. So now I can kill one of the n's because they both are in a square root. I don't know if you remember that from algebra, but you can only multiply or divide things that are in the same root. So I can kill an n. So where do I end up? Here's where I end up. confidence interval formula for percentage is p hat give or take z square root of p hat q hat all over n. So that is exactly the formula. It accomplishes the exact same thing that this does, just for percentages instead of means. That's all. They look very similar. How do you find this the same way? You got to tell me how confident you want to be I can find that. Is that cool? All right. I'm done. I think I'm done. That's plenty for today. I feel like that is plenty for today, especially considering I don't give you guys breaks because I'm an asshole, but I'll let you out early, so hopefully nobody will complain. All right, guys, so let me know if you need to hang out for a bit, if you have any questions. The quiz is supposed to unlock at 3. If anybody wants to start right now, let me know. I can go unlock it right now. Or else, you know, just wait till it goes around. What can you find with that formula? Oh, so we can do the same exact thing we did here. So if I have a sample and I have like 17% of the people I talk to like jelly babies, I can then make a confidence interval for the true percentage of all people that like jelly babies. So this formula allows me to do a confidence interval for a mean. This formula allows me to make a confidence interval for percentage. Exactly the same interpretation in everything. Is that cool? Does that make sense? Okay. It's all the same interpretation. It's just percentages instead of means. That's all. I will try. Is everybody else all right? You guys good?
For the test, you said that we'll be given the formulas, or do we have to memorize the formula?
No, the formulas are on the quiz.
Okay.
Yeah. Anytime. And I think it unlocks at 3, so nobody said they wanted it open now, so it's like 3 minutes away. No, the grades don't have our homework factored in. Yeah, what I need to do, what I used to do in the before times is after the second test, I would give out grade sheet summaries. And one of the things on the grade sheet summary would be what your average is, what your average would be with no homework, and what your average would be with all the homework. So I can actually still do that. I just have to find time to sit down and do that. Because I don't know the real story until the end of the semester, like you're saying, Rhiannon, about the homework. So it's, can we ask for that in office hours? Yeah, the only problem is I haven't really downloaded the Canvas spreadsheet to look at homeworks and the situation there. So I don't even currently have a handle on what the range is for everybody, to be honest. So I will work on that. Being online, I'm off track from my normal stuff that I do. So I'll try to work on that. And then I could just make it a thing in your grades. So your grade saying current overall grade, what it would be with no homework, what it would be with all homework. So you can just see it as if just a grade up in Canvas. That's what I did last semester at some point. Of course, last semester was crazy. Just trying to learn how to do anything. All right, everybody else all right? Y'all good? I'm headed out. Gotta go to lunch. Bye, everybody.